do this guy. So I think we're going to need to start off. We've got a roller. It's not labeled. I'll call it A. Why not? And I'll call this B. So I've got a roller at A and a pin at B. I'm going to have to find those reactions before we can get started. So I'll come over here and we'll draw a quick free body diagram of the beam. And I will assume, well not assume, I will put positive shear at A and positive shear force at B. Bless you. And then up here, I'll have on the left side an 8 kilonewton force, and on the right side a 4 kilonewton force. And then I'll replace this distributed load with a concentrated equivalent. So the area of the load is rectangle, so it'll be base 4 meters times height 4 kilonewtons per meter. So that's going to be 16. And it will land right in the middle of this, which is also centered right in the middle. So it will be, let me see if I can write these dimensions. So from A, I'll have 1 meter. And then the distance from here to here should be 3 meters. Is that right? And then 3 meters. And then 1 meter. I think that's all the dimensions. So let's sum moments. Again, either side would work. I'll just start with A. So I'll sum moments about A and make sure the beam is in equilibrium. I'm going to use right-hand rule. So about A, all my forces are going to create what kind of moment? Negative. So the first one will be 8 kilonewtons times 1 meter. Then 16 kilonewtons times 4 meters. Then 4 kilonewtons times 7. And then the shear force at B times 8. So from all that, I can find my shear force at B. I believe it's going to be negative. I don't know what it's going to be.
Negative 12.5.
Negative 12.5. Anybody else get that? Yes? Excellent. So the shear at B is negative. So now we'll sum forces in the y direction. And let's see what we've got. So I'm going to assume up is positive. So shear at A is up, positive. Shear at B is down, negative. And all my forces are down. So that's minus 8, minus 16, minus 4. So the shear at B should be 14.5? 15.5. And we already know that the moment at A is 0 and the moment at B is 0. So I've got my starting points for my graph. So let's draw the template. There's my starting point A, my ending point B. What else do I need to keep track of? Well, I've got a couple of point loads. So those are points I know my shear is going to change. So let's add those in. There's one there. There's one there. And then I see that I've got no load, and then this distributed load starts and stops. So I need to add those to my template too. I think that's enough for right now. So I'll come first and I'll mark my positive x-axis, my positive shear. All my units will be in kilonewtons. Let's mark what I know. What is the shear at A? 15.5. Positive. What's the shear at B?
Negative 12.5.
Negative 12.5. So now I can apply my relationships, which we've already done a few times. We know that the change in shear is going to be the area under the load curve, and that the slope of the shear diagram will be the load. Also, don't forget that as we go by or go past a point low, we know the shear will change equal to that value. So let's use all those to our benefit. What is the change in shear over the first meter? The area of the load curve in the first meter, which is 0. So there's no change. Stays 15.5. What's the slope of the curve? What's given by the load, and what's the value of the load? 0. So we have 0 slope. Now as I go from the left side to the right side and go under this force, how much does my shear change? Changes by negative 8 kilonewtons. So 15.5 minus 8 is 7.5? 8.5. Is it? 7.5. 7.5, right? Is it? Oh, bless you. 7.5. And the change from there to here over the second meter, staring at the curve, which is 0, so it stays there. And of course, the slope of that curve is given by the load, and the load is 0, so curve with 0 slope. So far I've got kind of like a little step going here, stepping down. What's the change in shear between 2 meters and 6 meters? Will be the area of this part of the curve, which is equal to 16, and that's positive or negative? Negative. So what's 7.5 minus 16? Negative 8.5. And the shape of the curve is given by the load, and the load is constant and negative. So there's your constant negative slope. What's the change in shear from this point to this point? You go up and look at the area on the load curve, which is 0. So there is no change. It stays 8.5. And the slope, well, it's given by the load. The load is 0, so that's a horizontal curve. Then as I go from the left side to the right side, my shear changes by how much? The value of my force, which is minus 4. 8.5 minus 4 is negative 12.5. Now this is looking good. And then the slope of the curve is given by the load. The load is 0, so I can connect those two dots, and I've found my way home. So comforting when you find your way home. Great, isn't it? Anything unique happen with our shear diagram? You crossed the line. You crossed the line. So where did we cross the line? What distance x1 did we cross the line?
Halfway in the middle of that.
Negative, Ghost Rider. The pattern is full. What's the change in shear from here to here? It starts at 7.5, ends at 0, so the change in shear is minus 7.5. If you extend this up and look at the area under the load curve, what is the area under the load curve there? It's a rectangle, base x1, height 4, minus 4 x1. Those two things are equal. Solve for x1. What's 7.5 divided by 4? 1.875. Why do I need that number? Yeah, it only tells me the moment's max. I'm going to need it to find this area to find my change in moment. Oh, I've run out of time. Sorry. I went a couple minutes over. You know what? If you don't mind, I can either finish this up now and you can stay, or you can not, and I'll finish it up at my desk and I'll put out the solution. Or I can pick it up next Tuesday, which you completely will forget about between now and then.
Yeah.
So I gave you too many options, I think.
Yeah.
I think I'll just continue, but you're free to leave. But we'll look at you as you go out. No. So I'll establish my positive axis and my positive moment, and these will have the units of kilonewton meters. It shouldn't take but another minute or so. So at A, I know I have a 0 moment. At B, I have a 0 moment. And remember, our values are that the change in moment, our relationships are, is the area in the shear diagram, and that the slope of the moment is the shear. We don't have any applied moment, so there won't be any kind of dramatic change. So what is the change in moment over the first little bit of area here? Well, it's a rectangle, base of 1 meter, height of 15. So I should get to 15.5. And the slope is given by the shear. The shear is constant and positive. The change in moment over the next meter is this area under the little curve. I'll hatch that a little bit more. What's that area?
7.5.
Yeah, it's base of 1, height of 7.5, so add 7.5. So 15.5 plus 7.5 is 23. The slope of that curve is equal to the slope. The slope is equal to the value of the shear. You can see the shear is constant and positive, but slightly smaller than the one before. So your curve will kind of go down. I didn't really draw it to scale. I'll try to exaggerate it here. You see the break in the slope? Now the change in moment over the next segment is given by this area of the curve. And what's that? 1/2 base, which we just solved for, 1.875, times height, 7.5. What's that number?
37.
30?
Oh, sorry,
I can't do that in my head. It's like 6 or 7, something like 6 or 7, something. No, no one knows. Did all of our calculators leave?
Oh, I just found it was like 7.03.
So you add that to 23, you get something that's very close to 30. I'll just say it's 30. And what's the slope? Well, it starts off at a positive value and decreases to 0. So I'd swag me a little curve just like that. They actually have the same slope right there, but then the slope decreases to 0. Now, what's the area, the change, a moment from this point to here? What's the area of this part of the curve? Which is 1/2 base times height, 8.5. What's the base? Well, it's going to be 2.125, right? What's that? We're going to subtract that from 30. What are you going to get? 21?
Yeah.
And the slope is going to start at 0 and decrease to some negative value. So something maybe like that. In the next section, what do we get? What's the change there? It's this little area right here, which has a base of 1 and a height of, this kind of got out of whack. It's 8.5 goes here. So that would be 8.5. What's 21 minus 8.5? It's 12.5, isn't it? And we would have some slope. And then the final bit, the change is this area, which is 12.5. That brings us to 0, and the slope's a little steeper. So what's the maximum moment?
30.
30. Where does it occur?
30 meters.
At 3.875 meters from A. Right there. Okay. Thanks for the extra time. I'll give it back to you some other place. Hope I didn't make you late.